Hello all, we are in digital electronics lecture number 27. We are discussing about asynchronous sequential circuits, and from today we will start a new topic, that is hazards. Okay. And myself Dr. Kishanu Kundu, Assistant Professor, Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management. So, let us start. First of all, we will discuss what are the main definition of hazards. So, hazards are unwanted switching transients that may appear at the output of a circuit because different paths exhibit different propagation delays. Different paths exhibit different propagation delays. So, we will discuss hazards in for combination circuit and for sequential circuit. Already for combination and sequential circuit we have already discussed lecture videos, you can refer. Mainly in combination circuit, the output the present output depends only on the present state, right, but in sequential circuit the output depends on present state as well as on the previous state, that memory concept, right. So, hazards are the unwanted switching transients that may appear at the output of a circuit because different path exhibit different propagation delays. Okay. So, these are the hazards for combination circuit. A hazard is a condition where a single variable change produces a momentary output change when no output change should occur. Okay. So, there are three types: static 0 hazard, static 1 hazard and dynamic hazard. What are they? Let us discuss. First of is static 0 hazard. The output may go to 1 when it should remains at 0. It should remain at 0, but output is going to 1. So, that is called static 0 hazard. What is static 1 hazard? The output may go to 0 when it should be remain at 1, means the output should be at 1, but it is going to 0. So, that is called static 1 hazard. Next is dynamic hazard. What is dynamic hazard? It causes the output to change 3 or more times when it should change from 1 to 0 or 0 to 1. Okay. Here the output to change 3 or more times is changing, but it can be changed, the proper it should be changed from 1 to 0 or 0 to 1, but no, the output is changing 3 times more. Okay. So, that is called dynamic hazard. So, these are the hazards that we found in a combination circuit. First one is static 0 hazard, then static 1 hazard and then dynamic hazard. So, we will take an example for demonstrating the occurrence of hazard. Okay. So, assume here we have taken a circuit, you can see the inputs are x1, x2, x3 and output is y. So, here it is x1, x2 one gate, this is x2 bar. So, this is nothing but x3, x2 bar and it is the OR gate. So, y is nothing but x1, x2 plus x2 bar x3. This is a random example we have taken. Okay. Random example we have taken. So, now assume that all three inputs are initially equal to 1. This x1, x2, x1, x2, x3 all initially at 1, that we have assumed. Okay. Then consider change of x2 from 1 to 0. Now, x2 is changing from 1 to 0, okay, but x1 and x3 are same, x1 and 1. Okay. So, in the output momentarily may go to 0 if the propagation to the input is taken into account, right. So, previously it is 1, now we have taken a inverter, and we have now the value of x2 is 0, right. So, the circuit implements the Boolean function, you already have seen that y is equal to x1 x2 plus x2 bar x3. So, this type of implementation may cause the output to go to 0 when it should be remain 1, means here if all are 1 then the output should be 1, okay, but it is going to 0, means it is static 1 hazard, right, because the output should remain at 1, but it is going to 0. So, this thing we have to check here, see it should be 1. So, that is the static 1 hazard. Is it clear all of you? Because initially all inputs were 1, but we have changed the x 2 from 1 to 0, and when it is 1 to 0, the output momentarily going to 0, but it should be remaining at 1, but it is going to 0. So, that is why it is called a static 1 hazard. Clear? Okay. So, now this was the, we have written this in the sum of product, this is the form of sum of product form. But if we write this in the product of sum form, what will be remaining? This is the product of sum form. Okay. Here it is x 1 plus x 2 bar into x 2 plus x 3. So, the same circuit we have implemented now in the product of sum. Okay. So, if we implement the circuit in product of sum form, then what will happen? The output may momentarily go to 1, it should be remain as 0, right. So, this is nothing but as static 0 hazard, because previously it was a sum of product form, here it is a product of sum form, okay. And initially it should be, the output should be 0, but it is going to 1. So, this is the static 0 hazard. A third type hazard also known as dynamic hazard, causes the output to change 2 or 3 times when it is should be changed 1 to 0, 0 to 1. Already we have discussed about dynamic hazard. So, by using this example, we have demonstrated the static 0 hazard as well as static 1 hazard, right. Static 0 hazard means the output should remain at 0, but it is changes to 1. So, that is called static 0 hazard. And what is static 1 hazard? Output should remain at 1, but it is changing to 0 for certain conditions, right. That is called static 1 hazard. Okay. Now, we can discuss further. The occurrence of the hazard can be detected by inspecting the map of the particular circuit. Okay. So, just do the thing, we have taken this value na, x 1 x 2 plus x 2 bar x 3, x 1 x 2 plus x 2 bar x 3, this is the value. Now, if we put this x 1 x 2 x 3, 3 combination. So, how many 3 variable, how many combination? Total 8, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and triple 1. Okay. So, if we put this thing, though in this equation we will get the values here. For 0 0 0 output will be 0, for 0 0 1 output will be 1, for 0 1 1 0 1 0 output will be 0, for 0 1 1 it will be 0, for 1 0 0 again it will be 0, for 1 0 1 it will be 1, for 1 1 1 it will be 1, and for 1 1 0 it will be 1. You just put these values into this equation, you will find this truth table, and this truth table has been implemented here in the K map form, right. So, K map form, here we have taken this side x 1 and this is for x 2 x 3. Okay. Just put the values of 1 here. So, you can do one combination, this is one combination. Okay. Clear? So, the remedy of, for it is written, the occurrence of hazard can be detected by respecting the map of the particular circuit. So, this is the K map for the particular circuit. The remedy for eliminating a hazard is to enclose the 2 min terms in the question with another product term that overlaps both groupings. Okay. So, here this is one and this is one. So, here we have taken one overlapping here, this one, right. This is the main point, the remedy of eliminating a hazard. How hazard can be eliminated? It is to enclose the 2 min terms in the question with another product term that overlaps both the groupings. So, this is the overlapping of both the grouping. So, now we are finding this equation x 1 x 2, it was previously there, x 2 x 3, x 2 bar x 3 it will be there. Now, this one x 1 x 3 this is the overlapping term. Okay. This helps in eliminating the hazard, clear. Now, this final equation is x 1 x 2 plus x 2 bar x 3, we will write down here. Final equation is y is equal to x 1 x 2 plus x 2 bar x 3 plus this is x 1 x 3. So, this is x 1 x 3. So, now we will implement that in the circuit, hazard free circuit. See, this is nothing but a AND gate, this is x 1 x 2, this is x 2 bar, this x 3, so this will be x 2 bar x 3 and this is this is nothing but x 1 and this is nothing but x 3, this will be x 1 x 3. So, the final output will be coming as addition of these 3. Okay. The hazard free circuit is clear. So, this circuit was giving hazard. When the circuit is implemented in the SOP form, then it will be giving setting 1 hazard. When it is implemented in a POS form, that is what is giving as setting 0 hazard, and finally using the K map, and we have included the overlapping, one grouping has been included, and with that term we have eliminated the hazard. So, this is the hazard free circuit. So, here up to this we have discussed the types of hazard and how to remove the hazard. Now, hazard in sequential circuit. So far we are discussing about hazard in combinational circuit. Now, we will going for an example for hazard in sequential circuit. So, let us take and following asynchronous sequential circuit. Here this is, you can take any random example, here we have taken this circuit. So, this is x 1 and this is x 2, x 1 x 2, okay. This is x 2 bar and then x 2 bar y, this is nothing but x 2 bar y. So, final y is equal to x 1 x 2 plus x 2 bar y, clear. So, now we know if the values are like that, x 1 x 2 and small y, right. These are the input variables and this is the capital variable. So, 8 combinations 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 111. Okay. So, if we find the values, then we can do the thing, just put the values y, this will be 0, this will be 0, this will be 0, this will be 1, this will be 1, right, 1 this condition x 2 and y, right. Next, for 1 1 0 0 will be having 1, then 1 0 1 will be having 0 1 and 1. Okay. So, this value now have been implemented here 0 0 1 0, okay, and 1 0 1 1, right. So, now we have taken this. What is this circle? These are the stable states. See, this is 0 na. So, is column 0, wherever we are getting 0 we have circle it. So, this circle represents stable state, and now wherever we are having 1 we have circled the ones. Okay. So, now if we make a combination grouping, so this will this both one will be a grouped and this one will be a grouped. Okay. Clear? If the circuit is in total state y x 1 x 2, then 111 and input x 2 changes from 1 to 0, the next total state should be 110. Okay. But however, because of the hazard, output y may go to 0 momentarily. If this false signal feeds back into gate 2 before the output of the inverter goes to 1, the output of gate 2 will remain at 0 and the circuit will switch to the incorrect total state 010. It should be go to 110, but it will go to 010. This calamity emitter extra gate means this is the hazard condition, right. Circuit total state y x 1 x 2, this is 111, and if x 2 previously also we have changed x 2 from 1 to 0. So, if we change that should be it should be 110, but due to hazard it will go to 010. Okay, right. So, for this eliminating we have to include a extra gate. So, how we will include that? So, implementation with SR latch, and alternative way to avoid the static hazard is to realize the asynchronous sequential circuit with SR latches. Okay. SR latches we have already discussed in the previous lectures, you can find it out, right. So, a momentary 0 signal applied to S or R inputs of a NOR latch will have no effect on the state of the latch. A momentary 1 signal applied to S or R input of a NAND latch will have no effect on the state of the latch. These are the two conditions. One is for NOR latch, this is for NOR latch, and this is for NAND latch. We already discussed these NOR latch and NAND latch in detail. We have discussed these conditions. Just follow the previous lecture videos, you will be easily understand the concept. So, these are the two concepts, and now here we are considering NAND SR latch. For we know that this is the Boolean function, S is nothing but AB plus CD and R is equal to A bar C. So, these are the two conditions S and R, right. Now, since this is a NAND latch, we must apply the complement values of the inputs. So, we are complementing now that this is AB plus CD bar. So, this will be by de Morgan's theorem, we will be writing like that A bar into CD bar, and R it is A bar C. So, we can write down A bar C whole bar. Okay. So, now the result in the implementation is like that. See, this is A bar B bar, this is C bar D bar. So, now S is A bar B bar into C bar D bar, and this is A bar C whole bar, right. This thing only we have taken it out, this A B bar C D bar. Okay. So, now this is the input of S and R SR latch, okay, and this is the Q and Q bar. So, the output function Q is nothing but Q bar S whole bar. So, what is the values? Q bar A B bar into C D bar. Already value of S we have written here, right. S is A B bar into C D bar, right. So, you have written here this one, S is nothing but A B bar. From this we have this value we are getting, right. This is 1 second, this is nothing but we will write like this, this is A B bar, this is C D bar. Okay. So, S is nothing but this is A B bar into C D bar. Okay. So, like that we have written, this dash is the bar concept. Okay. So, the Boolean function of Q is nothing but Q is equal to Q bar into S whole bar. So, we have written like this. The above function may also be generated with the two levels NAND gate. So, this is A B C D and A bar C. This thing same thing we have implemented using NAND gate. Now, if the output Q is equal to 1, then Q bar is equal to 0. Obviously, if 2 of the 3 inputs go momentarily to 1, then the NAND gate associated with the output Q will remain at 1, because Q bar is maintained at 0. Okay. So, now essential hazard. Now, we will go for the essential hazard. Another type of hazard that may occur in asynchronous sequential circuit is called an essential hazard. This type of hazard is caused by unequal delays. This is caused by the unequal delays along 2 or more paths that originate from the same input, right. An excessive delay through an inverter circuit in comparison to the delay associated with the feedback path may cause such an hazard. So, what is the reason for hazard? Essential hazard? Excessive delay, right. Essential hazard cannot be corrected by adding redundant gates as in static hazard. Previously, we have included one gate, right, and we have eliminated the static hazard, but essential hazard cannot be eliminated like that. The problem that they impose can be corrected by adjusting the amount of delay in the affected path. So, we have to adjust the delay. We cannot include an extra gate and we can eliminate the hazard, right. To avoid the essential hazard, each feedback loop must be handled with individual care to ensure that the delay in the feedback path is long enough compared with the delays of the other signals that originate from the input terminals. Okay. The problem tends to be specialized as it depends on the particular circuit used and the size of the delays that be encountered in the various paths. Okay. So, these are the essential hazards, these are the references. Thank you.